The workshop in Ramat Hasharon smelled of gun oil and heated metal. It was late 1967, and Yisrael Galili stood before a disassembled FN FAL rifle spread across his workbench like pieces of a failed promise. Around him lay the collected evidence of a problem. Damaged magazines, sand-choked gas systems, reports from field commanders describing equipment that wouldn't function when personnel needed it most. The intense regional conflict had ended months earlier with a decisive Israeli victory, but the equipment analysis told a different story. Troops had abandoned their issued rifles mid-engagement to pick up captured Soviet AK-47s. Not out of preference for the opposition's gear, but out of desperate practicality. The AKs functioned, the FALs didn't. That simple, brutal fact sat at the center of every discussion in the nation's defense industry. Galili wasn't starting from scratch. He had spent years working with Israel military industries, studying the Kalashnikov system through its Finnish derivative, the Valmet M62. The Finns had taken the AK's core principles and refined them for Arctic conditions. Now Israel needed the opposite transformation, a tool that would function in heat and sand, that turned precision instruments into expensive clubs. The FAL's problem was philosophical. It had been designed for European environments, disciplined maintenance schedules, controlled settings, trained armorers. It was an excellent rifle for those conditions. But Israeli personnel operated in the Negev desert, where fine sand penetrated everything, where temperatures exceeded design specifications, and where the intensity of the situation left no time for the careful cleaning the FAL demanded. Galili picked up an AK bolt carrier. Heavy, overbuilt, with tolerances so loose that sand simply fell through the gaps instead of jamming the mechanism. It was crude compared to the FAL's machined precision, but it worked. Every time. That reliability wasn't accidental. It was engineered, just from a different set of assumptions. The challenge was clear. Create a tool with AK reliability, but chambered for 5.56mm NATO ammunition, accurate enough for national doctrine, and capable of accepting modifications for different roles. It needed to be manufacturable with the country's existing industrial capacity, maintainable by recruits with minimal training, and functional in conditions that broke everything else. Galili knew the clock was running. The defense establishment wanted answers, not experiments. They wanted gear that would never again force their people to trust their lives to captured equipment. The weight of that requirement sat in the workshop like a physical presence. He began with the Valmet receiver as his foundation, but everything else would need rethinking. The caliber change alone cascaded through every component: magazine geometry, bolt face dimensions, gas system pressure, recoil spring tension. Each decision created new constraints, new problems to solve. This wasn't innovation. It was systematic problem solving under the pressure of documented failure. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Yisrael Galili's background wasn't typical for an equipment designer. Born in 1923, he had grown up in the pre-state period, joined the Haganah, and learned engineering through necessity rather than formal education. By 1967, he headed the development team at Israel Military Industries, a position that now felt less like a career achievement and more like standing in front of an oncoming obligation. The specifications arrived from the Defense Forces as a list of non-negotiables. The rifle must fire 5.566 45mm NATO ammunition for logistical compatibility with Western suppliers. It must function in temperatures from 20 degrees to plus 150 degrees. It must continue operating with sand, dust and debris in the mechanism. It must accept both proprietary and AK pattern magazines for field flexibility. It must be producible with stamped steel components to enable mass manufacturing. It must be accurate to 500 meters with iron sights. Each requirement eliminated options. The 5.56 mm cartridge demanded a different gas system pressure than the 7.62 Teague's 39mm AK. The temperature range required special metallurgy. The sand requirement meant loose tolerances and easy field stripping. The dual magazine compatibility complicated the magazine well geometry. The stamped steel construction limited certain design approaches. The accuracy requirement demanded barrel quality that budget constraints made difficult. Galili worked with a small team, but the fundamental design decisions fell to him. He chose to retain the AK's long-stroke gas piston system because it kept propellant gases out of the receiver, reducing heat and fouling. But he modified the piston design for the lighter 5.56 cm cartridge, adjusting the gas port size and piston mass to achieve reliable cycling without overstressing components. The bolt carrier needed complete redesign. The AK bolt worked through rotation, with locking lugs engaging the barrel extension. Galili kept this proven system, but modified the bolt face for the smaller 5.56mm casehead, redesigned the extractor for the NATO cartridge's different rim geometry, and adjusted the cam path that controlled rotation timing. Each change required calculation, prototyping, testing, failure analysis, and revision. He made controversial decisions. The charging handle moved to the left side, breaking from AK convention. His reasoning: right-handed users, the majority, could charge the tool without breaking their grip. Critics called it unnecessary deviation. Galili called it obvious once you watched people actually use the equipment. The folding stock was another departure. The AK's underfolding stock was simpler, but Galili chose a side-folding design that preserved the cheek weld height and allowed operation with the stock folded. It added complexity and cost. It also added capability that field commanders had specifically requested after operating in vehicles and confined spaces. Material choices reflected the nation's industrial reality. The receiver came from stamped steel sheet, formed and welded, faster and cheaper than machining, and actually stronger under impact. The barrel was chrome-lined for extended life in desert heat. The furniture was initially steel and wood, later plastic when materials improved. Every component specification was a negotiation between ideal performance and achievable production. The pressure wasn't just technical. The security situation demanded self-sufficiency in production. The Galil needed to succeed not just as a design, but as a domestic industrial program. Failure meant continued dependence on imported gear that had already proven inadequate. The entire project carried strategic weight beyond its mechanical function. Galili worked through 1968 and into 1969, building prototypes, testing, braking, redesigning. Each iteration refined the balance between reliability and accuracy, between weight and durability, between simplicity and capability. The goal wasn't perfection. It was sufficiency, a tool good enough to trust your safety to every time, without exception. The Galil's operating mechanism is a study in controlled energy. Understanding how it works requires seeing it as a system of forces, materials, and timing. Each element precisely calculated to convert chemical energy into mechanical motion and back to chemical energy again, 60 times per minute if needed. When the trigger releases the hammer, it strikes the firing pin, which crushes the primer in the cartridge base. The primer ignites the propellant, generating gases that expand rapidly, reaching pressures around 50,000 psi in milliseconds. These gases push the projectile forward through the barrel while simultaneously pushing backward against the bolt face. This is the moment of maximum stress on every component. The barrel is locked to the bolt through rotating lugs. The projectile is gone and 400 meters downrange before the bolt even begins to unlock. This delay is critical. It allows chamber pressure to drop to safe levels before the spent casing is extracted. Open too early, and the case head separates, jamming the mechanism. Open too late, and you sacrifice the cycle rate and add unnecessary stress to components. The timing happens through the gas system. About midway down the barrel, a small port bleeds off a portion of the propellant gases into a gas tube. These gases strike the front of the piston, driving it rearward. The piston is attached to the bolt carrier, so this rearward force pushes the entire carrier backward. As the carrier moves, a cam path on its interior surface acts on a cam pin in the bolt, forcing the bolt to rotate and unlock from the barrel. This happens in sequence, not simultaneously. First, piston moves, carrier moves, bolt rotates and unlocks. Then, carrier continues rearward, extracting the spent casing, compressing the return spring, cocking the hammer. At the rear of travel, the return spring's stored energy reverses the carrier's direction. Forward motion strips a new round from the magazine, chambers it, and the cam path rotates the bolt back into locked position. The cycle completes when the bolt locks and the hammer catches, ready for the next trigger pull. Galili's specific engineering decisions shaped every stage of this cycle. The gas port diameter determines how much gas enters the system. Too little, and it won't cycle reliably. Too much, and you accelerate parts wear. The piston mass affects impact force and timing. The return spring tension must balance cycling speed against bolt closing force. The extractor claw tension must grip the case rim firmly enough to pull it from the chamber, but not so firmly that it deforms the case. The trigger mechanism is simpler than it appears. The trigger bar disconnects the sear from the hammer. On rapid fire, a secondary sear catches the hammer as the bolt locks, then releases it immediately. The tool cycles as fast as it can. On semi-automatic, the disconnector prevents hammer release until the trigger is released and pulled again. This selectivity lives entirely in mechanical geometry. No electronics, no complexity that can fail under field conditions. The magazine system required particular attention. Galili designed the magazine well to accept both proprietary 35-round and 50-round Galil magazines and standard 30-round AK magazines. This redundancy came from field experience. Captured ammunition and magazines might be the only resupply available. The well geometry had to accommodate the different magazine catch positions while maintaining reliable feeding from either source. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing began in late 1969 at military ranges across the country, from the coastal plains to the Negev desert to the northern heights. Each environment stressed different aspects of the design. The goal wasn't to prove the Galil worked under ideal conditions, but to find where and how it would fail under the worst conditions personnel would encounter. The sand test was particularly brutal. Engineers packed the mechanism with fine desert sand, the kind that had rendered the FALs inoperable, then attempted to cycle it. The first prototypes failed. Sand blocked the bolt carrier's travel. Galili widened the tolerances, increasing clearances between moving parts. The trade-off was precision. Looser tolerances meant slightly less accuracy, but the tool cycled through sand that would have paralyzed the previous equipment. Temperature testing revealed unexpected problems. In extreme heat, lubricants broke down, increasing friction. In cold, they thickened, slowing the action. Galili specified military-grade oils with wider operating ranges, but also designed the gear to function with minimal lubrication. The looser tolerances that helped with sand also helped with lubrication failure. The parts simply weren't precision fit enough to seize without perfect oil films. Endurance testing pushed the equipment through thousands of cycles without cleaning or maintenance. Barrels heated beyond design specifications. Springs fatigued. Extractors broke. Each failure generated design revisions. Galili strengthened the extractor, improved the barrel steel, and adjusted spring tensions. The target was 10,000 cycles between parts replacement, a standard the final design exceeded. The folding stock mechanism caused persistent issues. The locking system needed to be robust enough to withstand recoil forces while folded, simple enough for rapid deployment, and secure enough that it wouldn't unlock during use. Multiple iterations tested different locking geometries and spring tensions before finding the balance between security and usability. Field trials with active units provided the most valuable feedback. People used the rifles in actual patrol conditions, carried them in vehicles, and maintained them under field conditions. They reported that the charging handle placement made reloading awkward at first, but faster once learned. They appreciated the folding stock, but wanted a better cheek weld. They noted that the bipod was sturdy but heavy. One consistent complaint: people were using magazine lips to open bottles, damaging the magazines and causing feeding failures. This wasn't misbehavior, it was practical necessity. In field conditions, people needed to open rations, and dedicated tools were rarely at hand. Using the loaded magazine as a lever seemed logical to exhausted personnel who didn't carry spare implements. Galili's response defined his design philosophy. Instead of issuing prohibitions or expecting people to change behavior under stress, he solved it mechanically. He added a bottle opener, a simple stamped section integrated into the front sight base and bipod assembly. It cost almost nothing in materials or manufacturing complexity. It weighed a few grams. It prevented magazine damage that had caused actual equipment failures. Procurement officials questioned the addition. It wasn't in the specifications. It had no direct defensive function. But Galili understood something fundamental. Gear is used by humans, and humans are predictably unpredictable. Designing for theoretical perfection while ignoring actual use patterns was engineering failure disguised as specification compliance. The bottle opener stayed. It became the Galil's most famous feature, not because it was tactically significant, but because it represented a design philosophy. It said, "This tool is built for real people in real conditions, not for testing protocols and committees." It acknowledged that engineering serves humans, not abstractions. By 1972, after 3 years of testing and revision, the Galil was ready for adoption. It wasn't perfect, no equipment is, but it met every requirement and exceeded many. Most importantly, it worked when people needed it to work, regardless of conditions. That reliability was the product not of genius inspiration, but of methodical testing, honest failure analysis, and systematic refinement. The bottle opener reveals everything about the Galil's design philosophy when you understand the problem it actually solved. On the surface, it's absurd. A service rifle with a built-in bottle opener seems like a joke, a piece of trivia. But trace the engineering logic backward, and you find a sophisticated understanding of how complex systems fail. Personnel in the field were opening bottles with their loaded magazines. This wasn't occasional, it was widespread behavior across units. The magazine lips, designed to precisely guide cartridges into the chamber, were being used as pry bars. The resulting deformation was subtle, but critical. A magazine lip bent by a few tenths of a millimeter could cause feeding failures or complete jams. A mechanical failure in an engagement isn't an inconvenience. It's a tool rendered useless at the exact moment it's needed most. People were creating potential failures to solve an immediate need. They weren't being careless. They were being rational within their constraints. In field conditions with limited equipment, you use what you have. The traditional engineering response would be to strengthen the magazines, add warnings to user manuals, or improve training. Galili chose differently. He accepted that people would continue the behavior regardless of orders or education. Instead of fighting human nature, he designed for it. The bottle opener required minimal modification to existing components. The front sight base already needed mounting points for the bipod. Adding a stamped cutout required no additional parts, negligible additional machining, and no weight penalty worth measuring. The modification cost was essentially zero. The benefit was preventing an entire category of malfunction. This decision reflects a deeper engineering principle, design for how systems are actually used, not how they should theoretically be used. The gap between specification and reality is where most systems fail. The Galil succeeded because Galili designed for reality. The same philosophy appeared throughout the gear. The dust covers loose, fit allowed sand to fall through rather than pack and jam. The oversized trigger guard accommodated gloved fingers or cold-numbed hands. The charging handle's left-side placement acknowledged the needs of the majority. The magazine well's dual compatibility recognized that field resupply is unpredictable. Each feature represented design thinking that started with actual use conditions. The bottle opener became symbolic precisely because it was so clearly functional rather than ornamental. It couldn't be dismissed as decoration. It solved a real problem in the simplest possible way. It demonstrated that Galili understood his users completely, not as idealized personnel from manuals, but as tired, thirsty, resourceful humans who needed their equipment to work despite, not because of, perfect conditions. Historians often focus on the Galil's mechanical innovations, the modified gas system, the improved accuracy over the AK, the folding stock design. But the bottle opener tells the more important story. It says that good engineering isn't about technical sophistication. It's about understanding the complete system, including the humans who interact with it. The final curiosity isn't that the Galil has a bottle opener. The curiosity is that most gear doesn't, despite personnel having the same need across every organization in history. Galili's innovation wasn't the stamped metal cutout, it was the willingness to acknowledge and solve a problem that existed outside formal specifications. This is why the Galil worked when the FAL failed. Not because it was more accurate or more powerful or more advanced, because it was designed for reality, for sand, heat, minimal maintenance, field scavenging, and tired people who needed to open their rations. Every design decision, including the bottle opener, served that fundamental purpose. The equipment that emerged from this philosophy was unremarkable in most specifications. Decent accuracy, acceptable weight, standard cycle rate. But it was remarkable in the one specification that mattered. It functioned when the trigger was pulled every time, regardless of conditions. In the end, that's what effectiveness actually means. The Galil entered service in 1972 and remained the standard infantry rifle through the 1990s. It served exactly as designed, reliable, maintainable, functional under the harsh conditions of regional challenges. Personnel trusted it. That trust, earned through performance rather than specification, represented the ultimate validation of Galili's engineering approach. The gear saw extensive field use during the 1980s, where its reliability in dusty urban environments confirmed the design priorities. While other nations' equipment required frequent cleaning and maintenance, the Galil continued functioning with minimal intervention. The same loose tolerances that made precision enthusiasts uncomfortable made frontline personnel confident. In high-stakes situations, confidence in your gear's reliability is worth more than slightly tighter groups at long range. International adoption followed. South Africa manufactured the R4 and R5 variants under license, adapting the design for their specific needs. Other nations purchased Galils for their forces. The gear's reputation spread not through marketing, but through user reports. Those who had carried the Galil recommended it. That organic validation meant more than any sales literature. The Galil's influence extended beyond direct adoption. The design philosophy, prioritizing reliability over refinement, designing for real use over theoretical perfection, solving problems that existed outside formal requirements, affected how other nations approached equipment development. The bottle opener itself became famous, appearing in design discussions as an example of user-centered engineering. By the late 1990s, the forces began transitioning to more modern designs with different capabilities. But the Galil's phase-out wasn't due to reliability failures or design shortcomings. It was replacement by newer technology, not remediation of problems. The equipment had served its full intended lifespan without the catastrophic field failures that had prompted its creation. Israel Galili's contribution extends beyond the specific tool bearing his name. He demonstrated that effective engineering starts with understanding the complete system, including human behavior, environmental conditions, and operational constraints, rather than starting with theoretical ideals and hoping reality conforms. The bottle opener was a small detail, but it represented a fundamental approach to design that produced equipment people could trust. The lesson is applicable far beyond firearms. Any system used by humans under stress will be used in ways the designers didn't anticipate. Fighting those use patterns through regulations, training, or warnings rarely succeeds. Designing for them, acknowledging reality and adapting to it, produces systems that actually work in practice rather than just in testing. The Galil worked because Galili understood that engineering isn't about creating perfect systems. It's about creating systems that function reliably under imperfect conditions. The desert sand, the exhausted personnel, the damaged magazines, these weren't problems to eliminate through better training or stricter protocols. They were design parameters to acknowledge and accommodate. Today, the Galil represents a specific moment in engineering, the transition from precision-machined European designs to robust, field-maintainable systems designed for large-scale use and harsh environments. It captured lessons from the AK, refined them through systematic testing, and added innovations driven by actual use experience. The result was gear that fulfilled its purpose completely. It worked when people needed it to work. The bottle opener remains the enduring symbol, not because it was tactically crucial, but because it encapsulated a design philosophy that valued practical effectiveness over theoretical purity. In a field often dominated by specifications and formality, Galili added a bottle opener because people needed to open bottles. That simple acknowledgement of human needs made the difference between gear that worked on paper and gear that worked in reality. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to translate another technical history script, or perhaps analyze the engineering of another famous piece of equipment?